So this will sort of split 60-40 or so between a sort of global overview of superstrata and then into the newer results. So let me just start by saying, what's the basic goal? In contrast to a lot of the sort of stuff we've been hearing in Euclidean sections of quantum gravity, the whole idea here is to use some UV completion of gravity to actually capture the actual microstates of a black hole. And in particular, very much motivated by the idea that we're trying to construct the gravity jewels of the microstates of the D1, D5 system, especially those that were counted by Strominger and Waffe that started this whole new phase of the microstructure of black holes. So what in particular superstrata are, and microstate geometries in general, is the idea is you want to start off by looking for oh, that was strange. Okay.
There's something with the YouTube is not starting. I mean, it says it's starting, it's recording, but it's not on YouTube yet. So
okay. So basically the goal is to look at, in this context, at large-scale coherent families and see what they produce in the way of smooth geometries. And so the sort of cartoon of that is to think about some highly coherent set of excitations on the D1, D5 system and look for the geometries that are created by those beasts. So this talk is really in two parts, and I've given lectures in Saclay about the nitty-gritty of how you build superstrata, and they're available online, and I'm sure you can find the links on the QBH website. But here I'm just going to give a very broad overview of what they are, but particularly emphasizing the fact that now we have these geometries, you can go and use them and look at them as a useful tool for probing your horizon microstructure. And then the second part of the talk is really, or the last 40% or so, is to talk about these new streamal microstrata. I was looking for a better term, but it's not superstrata because they ain't super anymore. They're supersymmetry broken, they're non-extremal. And this is part of something we've been working on for quite a few years, trying to develop the ideas last year with Daniel Myers and Robert Walker, reducing the whole problem to 3 dimensions. And then we add to this what I call the cue ball or coiffuring trick, which I'll explain, which is really simplifying the problem to something you can actually get at, and then calculate some very simple but rather Rube Goldberg examples, and then try and see whether we can learn some broader lessons from those examples. Okay, so as David sort of described, I think very well a couple of days ago, what we're dealing with, I'll start with the field theory, is we're looking at the D1, D5 system. There's a stack of it, N1 D1s and N5 D5s with a total N, which is the product of the two, which counts the Sham pattern labels. As is well known, the open strings between these things create a CFT with central charge 6N1, N5. The basic core starting point is the Ramond ground states. They're a quarter BPS because there are two sets of different kinds of branes, each of which cuts the supersymmetry in half. And as David spent some time discussing, there is this sort of effective string description where you think of basically N1, N5 copies of the conformal field theory, but the theory comes with a twist operator. And when you make orbifolds, you can start linking these little string segments together, effective strings together. And then each Ramond ground state has some spin labels, which I'm not going to go into in any great length, so to speak. But there is one character that will play a major role here, which is the so-called maximally spinning string, which is the sort of universal ground state. It has a large angular momentum. You put all the spins up in each string bit, and then you add them all up, and you get a very large angular momentum. But also in this story, there are going to be two main characters. There's going to be this string segment or string bit of length 1 with all the spins up, and then there's going to be this 0, 0 guy, no spin at all, and it's going to have a generic length k. Now, it's not because these are particularly physically important examples, we're working in the realm of what is doable, and we can understand how to build superstrata using these things. We'd like to do something much more general, but this is what we can do. And so the class of ground states that we're going to be thinking about is where we have a certain number of copies of this guy and a certain number of copies of these guys with different lengths. And because of this orbifolding procedure, the total number of these string bits is N1, N5, but because you orbifold them together, now when you start counting them, this total number constraint gets partitioned amongst all the various bits. And we'll see this constraint turn up later when we talk about the supergravity dual. But that's the ground state. The superstratum is simply you add purely left-moving momentum excitations to this system. And so the right-moving sector remains in the ground state. There's 1/8 BPS states in the system, which are often referred to as the supergraviton gas, or at least the supersymmetric parts of the supergraviton gas. But the right-moving sector, I say, is in the Ramon ground state, so that still leaves you with half the supersymmetries. So you've got now 3 charges, each of which cuts the supersymmetry in half to give you 1/8. And the generic superstratum excitations are given by simply loading up this 0,0 guy with some Virasoro generators, and you can use the angular momentum plus or the L-1, J-1, 3, but you can load them up any number of times you wish to choose, but only on the 0,0 strands. And this is the generic superstratum state. And in some sense, when you look at that, this is an incredibly small number of states within the general Hilbert space. But again, it's the exercise in what we can do. But as we'll see, it is an incredibly rich and detailed collection of supergravity states. So it might be a statement to the effect of that it's hard within supergravity to see coherent states that go into the twisted sectors. We have ideas about that, but it's a major open problem to go beyond this. But as we see, it will still produce a very rich class of microstate geometries. Now, this excitations, when you start doing them, the M quantum number with the plus cranks up the left-handed angular momentum, or somebody's book the right-hand, no, this is left-handed. And similarly, this M here combined with a -1 and the N here combined with a -1 cranks up the momentum charge, which is the L0 eigenvalue of the conformal field theory. And these things are remarkably rich sets of states in the collection of BPS geometries, and we'll talk much more about what they actually entail. Okay, now microstrata. Naively, and this is a question I would ask in some sense for all the people working in the CFT. What I'm going to do in supergravity is basically put all possible combinations of left-moving and right-moving excitations in the supergraviton gas. They slam together, so naively, based on the left-moving dictionary and the right-moving dictionary, you would simply say, okay, take those same old states and now load them up with the left-moving Virasaros and exactly the same set of right-moving Virasaros with some appropriate combinatorial factors, and just do exactly what you did where you now allow coherent combinations of left movers and right movers. And coherent here just means these occupation numbers are all significant fractions of the total number n1, n5, so you have some coherence and therefore some gravity manifestation, or supergravity manifestation of this state. So all the supersymmetries are broken now because you've got left movers and right movers. There's no Ramon ground state within sight. And so the hope is, but I'm not sure whether this is strictly true, the holographic dictionary can be extrapolated from the BPS dictionary. You've got left-moving BPS and right-moving BPS. But the sort of murky territory in this identification is, of course, the obvious instability. If you slam left-moving strings into right-moving strings, then you run an amplitude for making a graviton. And so this is not necessarily a priori stable situation. In fact, if you think about the sort of motivations behind microstate geometries in general, we expect that this sort of decay should be part of the Hawking radiation of the microstate structure. After all, you expect non-BPS stuff to annihilate or run into each other and create radiation that leaks off into the gravitational field. So G mu stands for here anything in the gravity multiplet. But basically, this should be how microstate geometries ultimately radiate into Hawking radiation. So the first thing I'm going to do is I'm going to dodge this bullet. And the way I'm going to dodge this bullet is I'm going to stick it in an ADS box, ADS3 to be specific. And so whatever I get, it's going to be this system in stable equilibrium with some kind of, with its gravitational field and with whatever it's creating in the graviton multiplet. And ADS3 makes it even easier because you can't get much in the way of gravitational radiation in ADS3. So whatever it is that I'm going to build the gravity side of this. And morally, it should be something like this. But exactly what it is depends on, I guess, the equilibrium that is set up between these two phenomena. Okay. Yes, please.
Can you go back one slide?
Yep.
if you want to consider this right moving and left moving guys, don't you want to have separately the ones excited by J and L, and also ones excited by J tilde and L tilde?
I might probably want to do that too. So I wasn't thinking, I was imagining taking all possible linear combinations of these states with all possible Fourier coefficients. I'm really throwing this out as a question to the people in the ADS CFT community, because I'm going to build everything in supergravity, but if I just put together all the ingredients that I know that a superstratum is this. There's an obvious, what I'll call in a moment, an antisuperstratum, which is simply the other side. And I would think about a simultaneous coherent state made out of superstrata and antisuperstrata. This is the sort of thing I have in the back of my mind.
Do you have the same structure visible from the solution? I mean, do you see?
We'll talk about that. I've got to get there eventually, but I'm just trying to set the scene of, to some extent, where I hope the program's going to be able to go. I mean, the superstrata, superstrata are great because they give us a very nice stable zero temperature background that we can study the hell out of because it's stable. And so to go non-BPS and to follow the same thread of trying to get the Strominger-Waffe states and non-BPS, this is the kind of thing you want to try and do. And so I'm going to give you a really Rube Goldberg version of this, as you'll see by the end. But it will achieve something in this direction. And the real question at the end of this talk is going to be, what the hell's the holographic dual in the field theory? What Bogdan and Anthony and I have created. So I'm just trying to, thank you. So I'm just trying to set the scene with this. But I'm going to go back and talk a little bit about I've talked about the CFT. Now I want to talk about the supergravity. And so it's the same setup. We have a T4, which is going to completely disappear from the discussion. You can make it a K3 if you like, because you're going to compactify on the T4. And at the end of the day, you have some 6-dimensional supergravity with 32 supersymmetries initially. We're going to pair that back because of the background of D1s and D5s. And the 6-dimensional manifold is simply the common directions of the D1 and D5 and the spatially transverse M4. The T4 is gone. And then the important starting point, is really this Luhmann-Mathur sort of situation, which is you take the maximally spinning supertube or the maximally spinning ground state, and this ADS region, it becomes global ADS 3 times S3. And so this is the structure that's going to be with us all the way. Okay, so we start with 6-dimensional supergravity. This is the ADS formulation of it, but you can extend it using the sort of standard supertube construction to flat space. And basically, we're going to consider these slightly more general ground states, but we're going to make our life a little bit simpler in a minute. But basically, these more general ground states, goes way back to, I think, Luhmann-Mathur, but also the holography of this goes to Scandelis and Taylor and various other things. And I'll try and give more complete references by the end. But this set of ground states was still in the 8 supersymmetries regime. We're just putting more Fourier excitations of fluxes into the geometry, and it changes the shapes. Okay, now, there's one thing I want you to keep an eye on, which is going to play a role throughout the whole discussion. It's what I call the seed. So if you're thinking about a coherent state of open strings moving along the D1, D5 system, the first thing it sources is the B field that is sourced by strings. And so the leading order perturbative seed of every one of these solutions, which will then be non-linearly completed, the leading order in perturbation theory is going to be some component of the B field that is sourced by this lump of stuff. And then when you turn on the back reaction, it mixes into the Ramond-Ramond fields, into the axion, and into the dilaton. But the first starting point of all of these solutions was always that first layer of the seed that you put into the equations. And then the hard work and heavy lifting is to get the full back reaction into everything else. Okay, so superstrata and microstrata are simply either are basic momentum waves in this system. And so they're either left moving if they depend on V, or right moving if they depend on U. And so the classic superstratum, which involves only left moving excitations, gives you a coherent state which involves all the following harmonics. It depends on V precisely because it's a left moving state, And the quantum numbers m and n, which turn up here and here, just reflect the mode numbers, reflect the excitation numbers here. And then, depending on the angular momentum of the state and so forth, there are excitations on the sphere. But what you're supposed to see here is that this is a supergravity solution already sourced by arbitrary functions of 3 variables, because you get to specify exactly what fields have exactly what modes. You put it into the seed, you put it into the B field, and then you follow on, and you can solve the goal is to solve the BPS equations. The antisuperstratum is completely trivial variant on this. You just simply send y to minus y, and then you get a right-moving guy. And the modes now depend on u with some other quantum numbers. And with, oh, that should be a k twiddle as well. No, k is the same. It's the same fundamental 0-0 state. But basically now you're thinking about exciting right movers. And so a generic non-BPS supergraviton gas state is something which starts out with an arbitrary Fourier series in u, v, psi, and phi with these Fourier coefficients. And in particular, I'll rapidly turn this to t and y, but at the moment it's left moving, right moving. But the other thing to bear in mind is, just like when you make a mode on a drum, there's the radial dependence, and here the radial dependence is the radius here and the theta on the sphere. Once you've specified these mode sources, everything then spreads out as a function of theta and phi. So it really is genuinely, the most general thing is a function of 6 variables sourced by arbitrary functions and arbitrary Fourier series and 4 variables. Okay, so now when you get down to building it, and I'm not going to go into any detail whatsoever, you reduce the problem from the 2-2 supergravity to a 1-0 supergravity coupled to anti-self-dual tensor multiplets. The 6-dimensional geometry has u and v built over a space, the base space usually called, which is the radial coordinate and the spheres, the sphere S3. And it is sufficient for supersymmetry that this base be hyperkähler and this be a self-dual field. I'm not going to go into the BPS equations, but I just want to tell you what they are or what they involve. So there are lots of fluxes on this background, and they have electromagnetic potentials, and they have magnetic two-form pieces. And then there are warp factors in the metric. P is the primary one, and it's made out of these electrostatic potentials, at least in the BPS case. And then there's a momentum potential, turns up here, it gives you information about the momentum charge, and then there's an angular momentum vector omega. And all I'm going to say is that they're determined by a BPS set of BPS equations, and the miracle is it's a linear system of equations. And it's basically a linear electrodynamics in 4 Euclidean dimensions. It's really about as good as it could get. It's intrinsically solvable, although it's inhomogeneous, so you have to solve with non-trivial sources. And the fields, at least for superstrata, depend on, as I say, arbitrary Fourier modes in V and on the sphere. Okay, so all I'm going to say about this, and there's a huge background to this, is that this linear system of BPS equations and its solution, while far from straightforward, is now really well understood, at least for flat R4. And as I say, there are many, many references, and I'll get them at the end, but the sort of state of the art in some sense is this recent paper we wrote a couple of years ago, which gave us the most efficient algorithms for solving this BPS system. But it's a huge open problem to solve this anything other than for fluctuating superstrata on more general hyperkähler bases. We have examples on hyperkähler bases without fluctuations. In fact, that's a huge number of microstate geometries, but superstrata on non-hyperkähler bases is unsolved. And I keep saying this, it's like my Carthago delendum essay. It's the holographic jewels of multi-centered geometries are actually not understood. Okay, suffice it to say, we now have many, many families with B being flat R4, and the most interesting and most important physically are the deep scaling superstrata. And these have long BTZ-like throats, and they're smoothly capped off at large redshift and look just like a black hole in 5 dimensions. And as you saw in David's talk, and to some extent Sean's talk, this has been tested, what comes out of these geometries have been tested against holography very thoroughly, and they work remarkably well. So the workhorse of most of the analysis that's been done is actually a simpler geometry where we ignore the angular momentum, the J plus excitations, and simply work with what are essentially pure momentum excitations. And it's easiest also to take this parameter K to be 1, and they're called the 1, 0, n superstrata, and they depend on essentially a set of different Fourier modes, which are only indexed by this quantum number here, or the power here. Okay, now, all you're going to need to know for what I'm going to say is that these classes of superstrata, which are the sort of workhorse of probing the things, it's got 3 primary parameters. A is the Fourier coefficient that represents this set of excitations. And it's essentially governs the angular momentum of the state, because this is the only thing that carries any angular momentum. There's another Fourier coefficient, B, which is sort of a stand-in for the mean square of all the Fourier coefficients here. It's an RMS average, if you like, of all these things. But it's how much of the 0K state you've got. And there is this constraint I alluded to earlier, which generally relates the A squared plus B squared to Q1, Q5. So what you're always doing is sharing the charge, Q1, Q5 charge between A and B. Or if there are many B's, many BNs. And the third parameter is the weighted average of these BNs. It's weighted by n because this gives you the momentum charge. And so all you need to take away from this is that these geometries are going to be governed by roughly 3 parameters, and everything else is details. So the geometric features are set by these parameters, and in deep scaling geometries, this parameter A, the geometries have very low angular momentum, and basically this parameter A is much, much less than B. Okay, so ADS superstrata, basically satisfying asymptotic of ADS 3 times S3. You should think of them as really the 3-sphere fibering over some interesting 2+1 dimensional base. And we're going to really make this precise by the end. So we're going to suppress pretty much the discussion of the S3. It's going along for the ride. It's this fiber. And the really interesting stuff is in the 2+1 dimensions. And there is a scale, B. And if R is very much bigger than B, then it looks like global ADS, well, it looks like ADS3 asymptotically. And the thing to keep your eye on is the S1. And at R bigger than B, the S1's growing rate with in size with R. So the circumference is 2 pi R. But when R squared approaches QP, or R squared approaches B squared, roughly, or n times B squared, then the S1 size stabilizes, and it stays at a fixed radius governed by QP, and it enters this process, this ADS2 times S1 throat. And this geometry is exactly, very closely to BTZ. This is in fact what BTZ does, and this closely conforms to the structure of BTZ. So you have this long BTZ-like throat, and then what happens is when the scale hits around about A, you pass through this sort of bumpy region of detailed geometry, which we sometimes call the momentum wave, and then underneath that you see no momentum charge, and it reverts back to being a global ADS3 governed by the scale A. But the curvature here, the background curvature here is actually set by B, and it is precisely that, set by Q1, Q5. So that's the structure, and we call these capped BTZ geometries for obvious reasons, and the superstratum gives you these capped geometries. Okay, it's a straightforward process, at least for the superstrata, to what we call restore the ones and the harmonic functions. That changes the asymptotics to ADS3 times S3, and you can resolve the whole set of equations. And then again at large R, what happens is that there's the S1 again limits to a fixed size. It's governed by the radius, the y coordinate. And the S3 then combines with the radial coordinate to make R4 plus the time. The space-time is then asymptotic to R4 times S1. And I want to just point out that this S3 is not quite, the S3 down here, the ADS3 times S3 is not quite the same as the ADS3 times the S3 at infinity. There is a non-trivial boost that I'll say more about, having to do with how this vibration happens here and how it goes away up here. Okay, so as I've said, the important thing about superstrata and the fact that we can construct them is they're really, the other point I really want to make here is that they're very, very useful laboratories for studying near horizon physics. I'm just going to give a broad brush outline of some of the uses. And one of them I've said many times, so I'll be very brief. The first triumph of this sort of stuff is that it gets an energy gap that's consistent, precisely consistent with the CFT in the maximally twisted sector. In other words, you calculate the energy gap by looking at the longest wavelength you fit at the bottom of the throat. There's a redshift governed by the depth of the throat, which are these parameters B and A. And you look at the energy gap and you define it to be the longest wavelength you fit here, redshifted by the depth of the throat. And we'll call that E gap. You compute it for a deep throat. And you find that the E gap is always governed by this A over B parameter. And when you calculate in terms of the geometry, it's always the J left, which is over M1, M5. And there's a number of order 1. And so you get exactly the gap that you expect from the D1, D5 CFT. And in more sophisticated calculations, I think it was Joseph and Pierre did, you get the number as being 2 on the money. So
David.
David, sorry, David. Basically, this is the sort of broad brush picture, but you can, with precise geometry, get the number precisely right. So that's a major, so these geometries really are accessing the maximally twisted sector in some sense. Now, the other thing I wanted to sort of mention, but because it's also going to have an interesting counterpoint later, the thing that's really cool about some of these microstate geometries is that the wave equation is actually separable, which means you can do a lot of analysis. And so one of the things we did was we calculated the boundary to boundary correlator in the ADS3 part of this thing. In other words, the idea is you imagine pinging the thing with a non-normalizable mode and then seeing the response that comes back in the normalizable mode at infinity. And so you calculate what is called the boundary to boundary response function, which is the variation of the normalizable mode compared to the non-normalizable mode. And you can actually do this with some precision because you have a separable wave equation. And what you find is a very beautiful picture, which is not altogether unsurprising. There's a sort of, the ping realizes there's a BTZ throat, and so it disappears down the throat with a sort of thermal decay. These periodic spikes have to do with the fact there's a periodic Y coordinate, but basically it decays according to a temperature. And then a long time later, B squared over A squared, this M1, M5, it returns with a sharp, perfect echo. So when you do these kinds of boundary to boundary correlators, which you can do explicitly in this sort of thing, you find the thermal decay that you would expect with at least the left moving temperature in the BTZ throat. I think Ben might say more about this in his talk on Friday. But because there are no quasi-normal modes, there's no horizon, there's no decay. So everything comes back as a very sharp echo, a time scale set by the central charge of the CFT sometime later. So you get perfect, of course, information recovery. But this ping that comes back is a perfect image of pretty much what went in. And so it's this sharp echo just simply reflects the fact that this state is far from typical. And so basically you get a highly coherent waveform. There's no hint of chaos here, but wait for it, there will be. Okay, since this also came up, and I think Monica was asking a bit about this, I wanted to say a little bit more about this, the Epron RealSantos story. So we have these cap BTZ geometries in a 3-sphere. But if you put them into an asymptotically flat space-time, as we know how to do, you find something interesting happens, or something that definitely requires investigation. The point is, the time-like killing vector at infinity, the thing that you fiducially measure time with at infinity, when it goes into this microstate geometry, has what's called an evanescent ergo surface. It means that it's going null. It never goes space-like, but in this particular cap BTZ, at R is 0, and on the equator of the 3-sphere, it goes null. And then it goes time-like again. So evanescent ergo surface. And on those surfaces, this killing vector is tangent to the surface. So what Epron RealSantos said is that matter that's near that line, near that closed photon loop, if you like, will become trapped for extremely long times. You know, it's like the dust that collects under the sofa. Slowly but surely, it forms a black hole. But in this particular case, they thought this accumulation would lead to instabilities. But in a somewhat more detailed analysis, Marel, Michel, and Poom showed that this trapping will probably result, or argue that this will result into scrambling of matter into higher frequencies and into stringy states that move the geometry perhaps away from extremality. So another way to do this is you can use the fact that this geometry has this flat space structure, and we can actually analyze this. The kinds of things that were analyzed by Epron, Santos, and Real were rather simple microstate geometries, and they certainly weren't these deep scaling microstates. And now you can look for the quasi-normal modes that represent the decay of bound states in the cap into the flat space reservoir that sits at infinity. And you can actually do it quite accurately using a generalization of WKB methods. There's a little subtlety there that I'm not going to go into. And in fact, it goes back to some earlier work by Chakrabarty and others, and then we followed up on this. And I want to point out something, yes, this has reminded me to point out something. Remember I said that it's an open problem to do superstrata and anything other than R4, and in particular doing it in generalized hyperkähler bases. One of the most interesting ones to do is superstrata in a Taub nut base, because the decay here is into R41. It'd be interesting to see whether decay into R31 makes a difference, and for that you have to build superstrata on a Taub nut base. There are many reasons why this is a very interesting thing to do that hasn't been done. Okay, so basically what you can do is you can reduce this whole problem to an effective tunneling problem in a one-dimensional potential. And there are 4 features. First of all, there's the usual sort of centrifugal barrier in the cap. Then, because you've got a deep throat and a well, there's bound states in the cap. Then there's this huge barrier you've got to climb through, which is the BTZ ADS barrier. But eventually, when you get out into flat space, there's energy dilution. You know, the quanta in flat space can have arbitrarily low energies, and this causes a very, dramatic, in this scheme, the energy falls off infinitely far. And so you can study tunneling. And you compute the amplitudes of decay from states in here to states out here. And we find 2 important things, one of which is that exactly the long trapping states that Epron, Real, and Santos were concerned about have to have wavelengths less than the string scale. And that's simple to see naively, because to get trapped for a suitably long time, you have to be very, very, very close to the evanescent ergo surface. And that very, very, very close is much less than the string scale. So this is exactly, I think, reflects what Andrea and Don and Ben and Michelle were arguing too, that essentially, by the time you're getting trapped for a long time, you must be substringing.
Nick?
Yeah.
Can I quickly ask, can you remind me if the analogous study of Epron, Santos, and Real has been done in Superstrata?
Well, that's the analogous thing. That's pretty much what we were trying to do here. Felicity was part of this collaboration. So the starting point of this paper was really to actually do the superstrata calculation. That was the generalization of what they did, but using this more sophisticated technique.
Okay.
So that was really what this paper motivated this paper.
Mm-hmm.
So I think there could be some interesting follow-up things to do. As I say, one of the reasons why I really would like to know the Taub nut version of superstrata is because I would like to look at this into a 3+1 dimensional space and see if there are differences, because the energy fall-off reservoir really matters, whether it's R³ or R². But there could be some differences, but we find very reasonable decay amplitudes based on the gap and the conformal dimension of the operator and so forth. Okay, so the last sort of thing I want to talk about here is this whole geodesic story, which we heard something about from Sean. And I'm just going to, again, very broad brush, talk about what it is. You think about some family of time-like geodesics, and there's a deviation vector across them, and there's a proper time tau. And the whole idea of geodesic deviation is you look at relative accelerations between geodesics. And then from the relative acceleration, you infer the internal stress forces on whatever extended object you choose to throw in. And this is sometimes called the tidal tensor, which turns up in this stress. And so the standard story for a black hole is very well known. When you fall into a black hole, you get stretched head to foot, but you get squeezed side to side. But the other thing is that we learn in elementary school is it's extremely weak. It's set by the horizon scale for macroscopic black holes. But what we discovered a few years back is that in microstate geometries, the fact that there's a cap means that there are multipole moments for the gravitational field, and these come to dominate in the throat. And so in particular, what happens is as you fall in from some large distance high up the throat, it's not only the multipole moments that come to dominate, but it's also the fact you're hitting those multipoles at an ultra relativistic speed. and that further amplifies it. And in the simplest of these calculations, you find the tidal forces hit the string scale roughly, in the geometric mean sense, halfway down the throat. There was you can do some fine tuning to delay the onset a little, but in fact, before you hit the cap, the tidal forces on a probe drop from a long way away will be large enough to hit the string scale. And so originally we thought, oh, well, that's interesting. So therefore, matter thrown in becomes intrinsically stringy, but we didn't run with it further than that until Emil and I came along and we found something else, which we'll come to in a second. The small deviation, so what's really going on is the tiny deviations of from constant curvature BTZ metric are amplified by the ultra-relativistic speeds, and the infalling matter must eventually become intrinsically stringy. And so that's the sort of picture, and that's the picture that turns up on the conference logo. Okay, but it turns out there's quite a lot more that can be said, and that was what Emil and I did, and this nice talk by Sean discussed. The ultra-relativistic speed, when you part, means that you actually zip through the cap very, very fast. And so rather than receiving just this endless stretching, the string actually receives a limited amount of excitations. You should think of it more as like a hammer blow. And so you can do a sort of sudden approximation, and you can see what then happens. And so if you drop the strings in with some very low energy or relatively low energy, some excitation, I put the string tension back in to make it dimensionless. Then you find the string modes only get excited with occupation numbers of order 1. And there's a cutoff to what can be excited. And roughly speaking, it says, take the energy you threw in and blue shift the hell out of it as it falls in. And that tells you what the maximum mode number is that gets excited. And then you can actually calculate an expected oscillation number, an expected effective mass, or actually mass of the excited string. And so the string exits the cap as a much more massive string state. And as with all tidal phenomena, the energy for this excitation comes from the kinetic energy of the thing that's being tidally influenced. And so the return height turns out to be very low, much lower than the infall height. And so the string falls back, and it does it all again. So the cartoon is this. It falls in, it gets excited somewhere depending on the multipole moments in here. It hits the cap, it becomes very stringy, and then it has more mass than it has. It's now a massive, very massive state. And so it falls back and does it all again, and then settles down at the bottom of the throat. There's possibly some interesting things left over. I'll say more about this perhaps on Friday, because this highly excited string could emit massless or low mass string quanta, which might eventually emerge back out. So there could be a tiny, tiny echo, but basically you basically get very highly redshifted echoes. So this has really important consequences, I think, for trying to probe these geometries. This calculation that I advertised before was based entirely on a massless scalar field, and you can think of it as a shape mode on the T4. But the string calculation that we just discussed shows that essentially that resonant peak is gone. There is no return echo because the scalar becomes intrinsically stringy, and it just gets trapped. So this sort of hybrid of probes, scalar probes and stringy effects, tells you that even the supersymmetric smooth microstate geometries exhibit complete absorption of matter. And so the full answer to the sort of boundary correlators is that there's thermal decay and there aren't any echoes. It just gets absorbed. Okay, except, as I say, for these possibly tiny weak string emissions. And also the other thing that we now know how to do, which I want to advertise again, is that once you've got an excited string at the bottom of this thing, or excited state, there's a chance that you can figure out how to do the tunnel into flat space by these kinds of WKB techniques. So all of this to say, given the superstrata, you have many of the tools available to you to enable you to do some really interesting stringy calculations and perhaps decay calculations of states in the bottom of the throat, which may or may not get you at least very low temperature or epsilon temperature effects inside superstrata. Okay, so I've got about 20 minutes left. Let me say what we were doing here. So the goal here was really something that was set up by work I did with Daniel and with Robert last year, but we've really begun to exploit it, and we've finally struck some gold. So I'll tell you about what we've got.
So, sorry, can I ask you
sure.
something before you go on? So,
Sure.
so your conclusion right now is that for 0 temperature, quantum black holes, basically there are no echoes.
No echoes, well, very, very weak ones, because what has to get the echoes, this excited string has to chuck off a quanta, and it has to have enough energy, and it has to be high enough up that it gets out. So if there are any echoes, it'll be in the master spectrum of string theory, and it will be very, very weak and highly redshifted.
Can you estimate? Sorry.
That's
so
a
just
homework
to
problem.
follow up on that.
Sorry?
Yeah, go ahead.
Sorry,
finish your answer.
Sorry. No, I was going to say, that's a homework problem I was going to assign next Friday. The answer is, can you estimate? Yes, I think you can. That's the homework problem. Well, but more seriously, I think you can actually estimate. You have to do the calculation of the amplitude to emit this string. You have to then check that this string doesn't fall prey to exactly the same tidal disruption and excitation through as it goes through the bump. So it has to be sort of emitted in the later part of this trajectory. And then it'll get out to infinity, and then it'll be seen. And what it will be seen as is kind of interesting, because you expect that this is this string will be in the low mass spectrum, perhaps the master string. Oops, I've lost it, the statement. And so I've lost the statement where I wrote this. Okay. And so this string will probably be in the sort of standard model of particles, because that's the low mass. So you expect some standard model burst, but I'm betting it's incredibly weak, incredibly highly redshifted, and probably invisible.
But let me I kind of understand this a little bit better. So what you're throwing in is a very heavier string.
No,
is that right?
Anything, because what happens is it gains kinetic energy by falling in. It's down here. It is an ultra relativistic particle. So it's like not like you are using the superstratum or the black hole as a particle accelerator. And then it hits the bumps and does what, fragments into all sorts of stuff, and it comes back out as low mass stuff. So it doesn't require much energy here. The excitation spectrum is cut off by the amount of energy you throw in and the redshift involved. So there are parameters here that will give you some cutoff. So,
but if the energy is very low, it cannot get very close to the.
No, indeed, nothing will excite. So if this is arbitrarily extremely small, nothing will happen. But it's a competition. How much energy you put in, redshifted, is it enough to give you string scale excitations? So there is a cutoff here. But for I think an accretion disk has probably got matter with enough energy in it.
Right, but if you have like a graviton with the Hawking temperature,
no. And everything I've said is so. Remember how I started this? I was thinking about some. I don't think if I thought about a graviton scattering at Hawking temperature, I don't think it's got enough energy. In fact, quite the opposite.
That's what I'm thinking. Yeah. Okay.
I don't know, to be honest, but it's an interesting question. And as I say, the things that we've done in terms of probing these geometries, we did the simplest probe we could imagine was a string falling radially inwards. And Sean did another more complicated probe of a similar nature. But you can imagine spiraling things in with some angular momentum. You can imagine wrapping things around the throat. There are lots of probes you can do, hundreds of them. The difficult thing is to find the one that's going to tell you some interesting new physics.
Yep. Thanks.
Okay, so let me get on to my sort of second bit. And
Sorry, Nick, can I ask a question too?
Sure.
So I wanted to ask, can you estimate how much you would get back out from the string radiating? That's one thing. So you answered that. But can you also estimate? So what I would expect is that at the end you're getting the string trapped at the bottom.
Yep.
And so really, what's happening is you have a perturbed new microstate, right?
Absolutely. It's exactly what Andreas sort of was arguing for as well.
Right. But then this perturbed microstate is going to want to emit roughly the same order of magnitude of stuff that you put in, which it'll emit roughly from the place where it has back reacted, right? So basically, I would expect that roughly the mass that you pour in at the place that it's sort of being trapped will be sent out again in terms of redshifted photons. Is that something you would
it's a
agree with?
So then I think I would say that you now got some state with a slightly elevated temperature, and it will Hawking radiate. And in the superstratum
I see. Yeah,
regime, that Hawking radiation should be represented as a tunneling process from here into flat space.
Mm-hmm.
So I suspect that I'm opening up a whole bag of can of worms here. If it thermalizes, then it really does have a temperature, and then it should look like Hawking radiation. If it doesn't thermalize and it's a special state, it will just tunnel.
Mm-hmm.
But I suspect that it will thermalize into a tiny little bit of stringy plasma at the bottom, which will then do some analog of Hawking radiation out into flat space, all of which should be some kind of tunneling calculation in this framework.
Okay. And then one last question I had was how, so I know you did this particular calculation, and I know the follow-up calculation that was done just now is also, there's like specific, it's done in a specific setup, right? And how, so how general do you think this is for some arbitrarily, you know,
okay,
I know you haven't done the calculation, but
I also cannot conjecture because I don't have enough information about what non-BPS Schwarzschild microstate geometries look like. But you know, I think it captures certain really important elements, and the really important element is the fact that this, I think, is going to be kind of generic. Because you've got a microstate geometry, the ride is going to be bumpy, and it's going to be, the bumpiness is going to be greatly accentuated by the ultra-relativistic nature of the particles. So trapping is going to be an intrinsically stringy trapping, I think is a thing in all of them. And, you know, this suggests an echo, and I think plausibly there should be some kind of echo like this, because once you've got a stringy state, it can throw out low mass strings.
Mm-hmm.
So I think the broad brush picture might be generally true. But in terms of computations, all I can do is this. I want to get on to the second part, because I think that's why Emil got up early in the morning.
May I make a comment about this?
Sure.
So in these geometries that one has a very long throat, I think one might worry that if you accumulate energy at the bottom, it might collapse into a non-extremal black hole.
Okay. You could worry about that, but in the microstate geometry fuzzball program, it doesn't do a black hole. It just thermalizes into a complex fuzzball. And that complex fuzzball might be outside the supergravity regime, but it still should be some kind of complex fuzzball.
Well, that's, I think, a philosophical or wish list or wishful statement, but I'm just asking a more practical statement. So if you have these concrete geometries that you actually have, right? And you add some energy at the bottom, I think there is a calculation that one could do of the back reaction of this energy.
And hold that question. That's where I'm trying to go.
Okay.
There's a partial answer to Hans' question. So the point is, if you look at multi-center solutions, which are described by this DNF multi-center quiver quantum mechanics, you can compute actually the phase space available. So from a supergravity perspective, it looks like you have a throat which becomes deeper and deeper and deeper, and therefore, you know, you put some energy, and maybe the throat just wants to become very, very deep, and you know, be completely destabilized. This is like, you know, this Klebanov-Strassler instability, for example, which we found in Mariana Grania in the context of the De Sitter landscape. So if you put some energy, the throat will just go in. On the other hand, Jan de Boer and Scheer, and Dieter van den Blechen calculated the symplectic form on this space. And what they found was that the amount of phase space available at the bottom, even if it looks like you go from 1 kilometer down to 2 kilometers over a nice, big, fat, smooth throat, the phase space available is actually over the 1. There's not too much phase space. So the energy will not go to make the black hole deeper, to make the throat deeper. It will actually go to make excitations. But you don't have enough phase space, at least in the supersymmetric 3-center calculation they did using quiver quantum mechanics and quantizing multi-center solutions. This is some paper by Jan de Boer and collaborators.
So let me try and give you an answer that sort of, I think, addresses a lot of, there are many of us who do this and we have divergent opinions. But basically, I think you can pile up a certain amount of stuff in the bottom of one of these throats and treat it perturbatively or semi-perturbatively, and it doesn't change the geometry. The question is, what happens when you pile up too much? Well, if you pile up too much, there's going to be a phase transition. And then you've got to argue about what that phase transition is. And some people say, oh, it's going to form a black hole. The philosophy of the microstate geometry and fuzzball program is that black holes just simply mean you're using a theory with far too few degrees of freedom that cannot see what's really going on. And if you use string theory and you use at least 2B supergravity, then there are many, many more options, and it will explore a range of microstate geometries and perhaps stringy excitations of those things. I think a black hole is an impoverishment of the phase space caused by using too few degrees of freedom. And that's, I firmly believe, what my experience of microstate geometries and fuzzballs has taught me. So black holes are the last resort of general relativity, but once you've got some more degrees of freedom, the phase transitions are much more interesting and much richer. And I think that's what we're trying to get at.
I guess.
Okay, I'm gonna move on because I want to at least reward Emil for getting up early. Okay, so and then we can come back to questions at the end. So what we've decided to, we've been working on BPS things for a long time. There have been some very valiant attempts to get non-BPS things, but we really wanted to try and get non-BPS things that are in this D1, D5 system. Now, a priori, that's a nightmare because, as I said earlier, it depends on all 6 variables. It's possibly hard even for numerics. Even if you say, I want to study one Fourier mode, you got 4 variables. And basically, the goal I want to try and realize is at least somehow, some way, get a non-extremal microstratum by using what we know in terms of the holographic dictionary. I put it in ADS3, or we put it in ADS3, because that gives us events decay. And there are 2-step processes to doing this. The first is that using this work that I did with Daniel and with Robert last year, which is to reduce the problem to 3 dimensions, which you can do by consistent truncation. And then it's to borrow something out of Sidney Coleman's playbook, the cue ball trick, which is also the same trick we use in coiffuring, where it turns out that you can turn on excitations that do depend on time and do depend on non-trivial Fourier modes, but the metric and the Maxwell fields do not depend on time. They only depend on the radial coordinate. And the simplest example of these, which we managed to construct, still involves solving for 11 functions, but of 1 variable. And so I'm going to talk about that. So it's non-trivial, but from these very specialized examples, but I think we've still learned some interesting physics, and I want to convey one of the 2 or 3 lessons we've learned so far. As I say, we've only had these for a couple of weeks, so we haven't fully digested them. Okay, so basically the structure of these superstrata in general is usually some kind of cap BTZ and a 3-sphere that's fibered or not fibered in some complicated way. But in certain circumstances, you can make this picture exact, and that's the consistent truncation story. So the idea is you find a consistent truncation that reduces the dynamics of some of the microstrata to 3-dimensional dynamics. And it can be achieved for this 1,0n and 1,1n superstratum and antisuperstratum, and that's what we did in these papers. And so morally, it's sort of like these states that you can do, but now with k is 1 and with these n's. But m and m twiddle can only be 0 or 1. And now the important part about the word consistent truncation here is if you solve the dynamics in 3 dimensions, you can create exact solutions in 6 and hence in 10. So it's made things at least significantly simpler. And therefore, on all the magic of the consistent truncation is to deal with all the sphere stuff just as an automatic byproduct of the consistent truncation. And one of the other open problems I promised I'd try and advertise as I went was there are other consistent truncations. And I'm sure there are, but we haven't constructed them. Anyway, at the end of the day, when you do this consistent truncation, you wind up with a 3-dimensional Lagrangian. So this 3-dimensional Lagrangian, of course, has gravity. It has some Kaluza-Klein fields from the 3-sphere. There are 6 of them. There's Chern-Simons interaction, a Maxwell interaction, and then a handful of scalar fields. There's a matrix of scalar fields here and a vector of scalar fields here, and there's a potential. All you're going to need to know about this potential is that it has a supersymmetric critical point where all the scalars vanish, or at least they trivialize, and it has an ADS vacuum, and the gauge coupling that turns up here is inverted is the radius of the ADS in that vacuum. There's one other important feature. This potential has a flat direction, and that flat direction is a ground state, but it breaks, except for the central point where all the scalars vanish, it breaks supersymmetry. Okay, now we're still going to make it easier because that's still too many functions. We can reduce to what's called the 1,0n sector by imposing another EU1 invariance. Now, to give you a sense of what we've got, remember I said at the very beginning, there is a superstratum has a seed. And that seed is always the Nova-Schwarz field that you're turning on first and foremost. And here it is. This is the seed. And then these guys are three other scalars that respond. They are actually shape modes of the three sphere, but it doesn't really matter. They're just going to be other scalar fields that you just have to allow themselves to turn on. There are Kaluza-Klein electromagnetic fields. There are now only 2 of them because I've imposed this invariance. And so the game we're going to play, as I say, you do what you can, is we're going to use the cue ball trick, or the Coiffurian trick. You are just going to turn on some non-trivial phases in these scalar fields, possibly in Y and omega. And it turns out for consistency, you have to turn on a phase associated with this scalar field. And then if you do that, you can consistently write a system of equations where the metric and Maxwell fields do not depend on anything other than the radial coordinate. That's why I'm called the cue ball trick. And it's a very specialized Rube Goldberg kind of machine to do this, but it enables you to actually construct something that's non-trivial. And so that's what we're going to do. And in fact, the numerics becomes manageable just. And as Anthony really contributed to this collaboration in many, many ways, but he was the guy who really pushed this incredibly simple perturbation theory when you only have functions of the radial coordinate. Okay, so what you need to take away from here is that if you're in 3 dimensions, the metric ansatz is much easier. There are 6 metric functions in principle, but there are 3 coordinate invariances. So in fact, there are only 3 metric functions once you fix all those invariances. And there's a really nice way to do it where you write the spaces conformally flat. And then the other 2 functions, k and omega 1, turn up as scales in front of time and vibrations. And then I've written in this form for another reason. If you want to recover global ADS, which is going to be what's limited infinity, you take this coordinate psi to be this simple rational, simple form. And the functions in question, the way I've parameterized it, are very, very simple. And the whole point of using this coordinate psi is because in numerics, you want to set the boundary conditions in infinity. And it's useful to bring infinity to a finite point, which is psi is equal to 1. Okay, so the ansatz. So we're going to take one of these scalar fields, a complex scalar field, and we're going to let it have a phase dependence. So it's going to be non-trivial time dependent. And in particular, we're going to fold in this non-analyticity into it. So this is a nice, well-behaved field, at least semi-analytically, and a similar phase. There are 3 other scalars that go along for the right. As I said, they're shape modes on the sphere. The Maxwell fields, there are 4 more functions there. There's an electrostatic potential here, electrostatic potential, a magnetostatic potential, and that's about it. And then the metric functions. So here are the 11 functions you've got to deal with. The 3 from geometry, 4 from Maxwell fields, and 4 scalars. And as I say, the one to keep an eye on is this guy, because that's the guy that at leading order drives everything. And as I say, the cue ball trick, or the whole point about cue balls or Coiffurian trick, is that the energy momentum tensors and currents don't depend on time or the Fourier angle. And so everything's just a function of R. So that's what we spent a whole pile of time doing. And so the first thing to do is to look for the superstratum. And of course, it's relatively straightforward. The so-called single mode superstratum is simply given by choosing a value of n. And then every other field just gets slaved to the value of nu and turns up in here. The things to notice are that these scalars don't move. So the shape modes on the sphere are fairly impoverished. But basically, one shape of the sphere does change in response to this. And the electromagnetic fields I won't say anything about. And there will be a thing in this discussion I'll call the amplitude of the perturbation. And it's basically if I turn on a mode or turn on one of these oscillations, there will be an amplitude associated with it. Okay, now we look for solutions that don't have omega not equal to 0. So these will be genuine non-BPS things. We're going to impose the supersymmetric vacuum at infinity. And to make life easier, I'm going to choose the mode number here to be 2. And there's a stupid reason for doing that, but it's better than choosing 1. So the linear analysis tells you something really very useful to start with. And I'm only going to look at the scalars. The 4 scalars in question have conformal dimensions 1. There's 2, delta is 2 with degeneracy 2, and there's a thing, degeneracy dimension 4. But if you look at the modes for the thing that drives it, the scalar modes in ADS, then simply you find that in ADS there are normal modes and they have to have even frequencies. And so at 0th order or linear, you find that this function nu has to satisfy the hypergeometric equation, and the basic hypergeometric modes give you this sort of picture. This is the superstratum, and then this is the first excited state, this is the second excited state. And all the action gets scrunched up here, and it's because the coordinate xi tends, the cap ends at about here, and so all the throat and everything else is stuck, is compressed to the end. But having done this, you can start looking for solutions. And we did. We put alpha and amplitude to be modest. The biggest it can be is 2. And you find the exact solutions where omega naught is the superstratum, and then omega is almost 2. I'm going to talk about these frequency shifts in a minute, but this is the linearized result, and this is the exact result. And so we find solutions where these things wiggle in exactly the way suggested by linearity, but the frequencies shift. And the full solution looks like this. There are 11 functions. There's the function nu, which is the seed, and then there are the other 10. And the geometry is down here. This is the electromagnetic fields, and these are the scalars. The gold plots are the superstratum, and the blue plots are the non-extremal solution. We chose omega as 4 because we wanted 2 nodes. So you get a nice, interesting wiggle, and everybody wiggles in a nice, interesting way. But the important point is the solutions are very different from the superstratum. They are very non-trivial. So these things exist and are smooth at both ends. We found many, many solutions, but let me just sort of explain global features, and since I'm running out of time. Many solutions, there are 2 sort of amplitudes that you can mess with in this rather Rube Goldberg restriction. There's the original seed amplitude, but it turns out this shape mode seems to be independently activated and can be independently activated. So we're going to talk about both of them. At infinity, we impose the supersymmetric vacuum, and we want to see what happens inside. And then we explore the solutions as a function of the frequency, alpha and beta. For a given Q1 and QP, we find, and Q5, we find that the solutions we've got have more mass than the superstratum, the same charges. So that is really important, but they are non-extremal in this sense, that they are more massive than the corresponding superstratum. The frequencies of the smooth solutions actually depends on the amplitudes of the deformations. And in particular, for non-zero beta, the cap, actually, the solution of the cap explores the flat direction of the supergravity potential and manifestly breaks supersymmetry. So let me just show you the sort of way we actually found this frequency shift originally. It was sort of an empirical science. We started a search algorithm for various frequencies, and we found that basically when we did the search algorithm, it didn't want to converge at 2, but when we searched across frequencies, we found it dramatically converged what we call resonances precisely at some particular numerical value. We thought, okay, so there's a frequency shift. But then Anthony did this beautiful analytic analysis. So here's something that should sound very familiar to the superstrata aficionados. It's relatively straightforward to do the perturbation theory. So at 0th order, it's hypergeometric differential equations, and essentially it's linear order. At linear order, all those hypergeometric differential equations are homogeneous, so you find solutions. Then at higher orders, it's the same hypergeometric operators, but the right-hand sides are now sourced by nonlinear combinations of the lower order sources. So you just keep bootstrapping your way through this. And you can do the perturbation to rather high orders in alpha and beta. Amongst other things, we find that if the scalars at infinity are set to 0, so that they produce the supersymmetric vacuum, you find frequency shift formula that looks like that. The frequency really does shift, and it shifts in response to the amplitudes of the modes you've turned on. And in particular, this graph shows you, this is the dots of the numeric results looking for these, quote, resonant frequencies, and this is the linear order. So this is 3rd order or 4th order perturbation theory. So
Nick, let me just interrupt to say that you've got about 10 minutes left of the allotted. So you've been going 1 hour 5. You've had plenty of questions.
But I'd like to stop in about 5. I want to just, but I just want to give the flavor of the results. So the first learning thing I want to get at is that we have this really interesting new feature, which is the frequency of the mode shifts in response to amplitudes of other things. Perhaps not surprising when you bear in mind the nonlinearities of the solution. Okay. Now, so as I say, I think the important new physics we'll learn from this in the fully back-reactive geometry is all the natural frequencies of all the oscillations are nonlinear functions of the amplitudes of all the other fields. So I think this may have something to do or related to the mechanism by which the non-BPS microstate geometries transition to the more chaotic spectra. Because if everybody's frequency cares about the amplitude of everybody else, it can't do anything other than produce some kind of chaotic spectrum like this. Okay, so what I want to do now is I've given you a brief summary of the numerical results, but you can actually go quite far with perturbation theory. And so if alpha and beta are small, you can actually, third order in perturbation theory, try and match the third or fourth order in perturbation theory, match the numerics to the perturbative result. And so these graphs are the same 11 functions, and the blue is the numerical result, and the dashed red is the third or fourth order perturbation theory, depending on what we need to do. And the first thing you see is in the seeds and these solutions, everything seems to match absolutely perfectly. So it gives us huge confidence that our numerical results are correct. However, you also notice some differences, but these differences are entirely comprehensible. See, look at this difference. It's 10 to the minus 7. This is also about 10 to the minus 7. So the fact this stays 0 in perturbation theory, but is non-zero in the numerics, what's going on here, as I'm certain, is that these fields are only influenced at higher order in the nonlinear interactions. And so these haven't got turned on yet because we haven't gone to high enough order in the interactions. So the numerics and the perturbation theory agree perfectly, except up to these tiny, tiny deviations, because I think the numerics are much more sensitive to higher orders than we can go in perturbation theory. But everything else matches perfectly. So I want to just say a last little comment about supersymmetry in the cap. In superstratum, the scalars all vanish in infinity, and it's a nice supersymmetric ADS vacuum. In the cap, the scalars all vanish, and you get global ADS again in the cap, and the scalars all vanish. And so I picked a typical scalar, and you find that the scalar vanishes in the cap, and it vanishes in infinity. And so in the superstratum, infinity is a supersymmetric vacuum. The cap is also a supersymmetric ADS vacuum. But if you do this for microstrata, you find that in one particular example, you find that, yes, it's supersymmetric infinity and it vanishes, but this particular scalar is in fact, the vacuum tells you the vacuum in the cap, and you find that it is exactly exploring the flat direction of the potential. So supersymmetry is manifestly broken by this solution. Okay. Last gasp. You can recast or try and recast the masses of these things in the BTZ form. And so from holographic renormalization, you have a mass here and an angular momentum here, and you read it off from these coefficients. And I want to remind you that for global ADS, in this language, the mass is -1 and the angular momentum is 0. And this has to do with the spectral flow that goes from the ADS formulation to the flat formulation of a supertube or superstratum, and this m is -1 is the -1 of the Nova-Schwarz vacuum. But just remember the baseline for is m is -1. If you do a superstratum, you find for the n is 2, you find that the j is basically the QP, and it's limited by 4, and in fact you find m minus the magnitude of j is still negative, but at j is 4, it exactly saturates and you get the BTZ bound. So if you look at this picture for m minus the magnitude of j, you find that the supertube is down there, the superstratum is that entire curve, and it limits the extremal BTZ up here. The class of solutions we've been finding sit here. And interestingly enough, there seems to be a barrier to going higher. There seems to be a locus of CTCs that seems to occur about there. We've only got a few numerical examples, but the minute we try and go up here, we run into a CTC problem. And I can just show you the last picture. What tends to happen is that you have some beautiful regime down here. This is the coefficient d psi squared, and in our conventions, negative means it's a space-like curve. So there are no CTCs, but if you crank this up too high, you get into a CTC region. And so you get closed time-like curves basically when you try and cross this barrier. So these new microstrata are filling out this region, but it seems to be very hard to go above this bound. Okay, so let me finish. But maybe I'll just put them all up and just simply say, look, what we're trying to do, I want to do justice to some of the references in these slides. But we've got deep scaling superstrata. We have asymptotically flat superstrata. We have a very systematic construction of superstrata, and we have precision holography that maps the superstrata back into the CFT. I wanted to advertise that superstrata are really good laboratories for near horizon microstructure. The instabilities we understand in terms of scrambling of states. The green function can be used to do thermal decays. We can understand bound states and tunneling. And tides and tidal scrambling and tidal trapping give us a whole new perspective on this story. So we've come a long way since in the last 6 years in the study of superstrata. But I think there's a whole new universe of non-extremal microstrata out there that we are actually going to be able to explore and study and perhaps see whether we can find something that is genuine. These are genuinely non-BPS and genuinely non-extremal, but strongly non-extremal and strongly non-BPS. And I'll stop there.
Thank you very much, Nick. Very nice talk. So I'm sure we'll have more questions. So please, anybody who wants to ask further questions, feel free to go ahead.
We had a small comment, but listening to this last part that Nick was saying about the CTCs, I was reminded of an old paper of Jimon and Horava, where they looked at over-rotating Gödel universes. They found the CTCs come, and just about the CTCs were, when they were about to come, you get some branes which come down instead, and they prevent you going into the CTC domain.
Yeah, I think part of the problem here is I tried to stress as I was going, we are doing something so incredibly specialized. As I said, it's a very Rube Goldberg set of solutions, and I can say just a tad more about that. What we're doing is, if you think about the superstrata as being purely left-moving solitonic waves, and the antisuperstrata as being purely right-moving solitonic waves, what we've done is we've moved the solitonic waves or coherent waves inside the light cone. And so these are a big blob of, that's what it means to have omega positive and non-zero. Zero is the superstratum, and if you can move inside the light cone, and increasing omega just simply tilts you more inside the light cone. So these things have a very high momentum, but they're also still locked into this superstratum form. And so they are very, very specialized states. So frankly, it doesn't altogether surprise me that we're having trouble getting above this bound. What we did, how to put it, I tend to think of this paper that we're about to write and this result as a proof of concept. We're showing that you can use this technique to build non-supersymmetric things, things that are non-extremal. But I think there are a lot more interesting things out there that we should be able to find that maybe we'll be able to push this bound and go out here. In particular, omega is negative is another one. That was where you start making the states which are now looking more space-like. What does that mean? It looks like the states that would result from an annihilation of superstrata and antisuperstrata and settle down to a time-independent solution. The reason why we stayed the hell away from those is because the linear order stuff involves lots of logarithms and high order logs. And so the logs are a bit of a nightmare numerically. So we decided to sort of go into a regime where the logs only appeared at very subleading orders. So to prove that we could do this, we wanted to just try and keep it as simple as possible numerically. But I think there are much more interesting physical solutions out there. And in particular, my favorite one, which I think we'll be able to do, is, let me just see if I can find it. It's where you have an antisuperstratum. Remember, I sort of said this thing there. There's trouble with turning every transition into a PDF file. Basically, you can have an antisuperstratum and a superstratum. So that's this guy. But if you make m twiddle equal to 1 and m equal to 0, then this antisuperstratum and superstratum talk to each other only at third order or so in the perturbation theory. So in other words, you've got a superstratum going one way and antisuperstratum going to the other, but because you put them in some sort of almost nearly orthogonal channels, their interaction is mild, and therefore you might be able to actually do that kind of calculation. That's hard, it's 13 functions or something, but it's doable, I think. And so all this to say, you should look at what we're doing here as a proof of concept rather than saying, I've got these fantastic physical solutions. What we've done is we've shown that you can make these remarkably interesting microstate geometry, remarkably interesting geometries that are not BPS, that are part of the superstrata, microstrata story, but as yet we're not getting as strongly non-BPS as we would like. But I say that the things we're learning, these frequency shifts and things like that are really kind of interesting. They're telling us about how, when you make these things interact in a non-BPS way, how the spectrum changes and how the excitations of one state influence the other states.
No, I agree. This looks very fantastic. I mean, I'm very impressed by the kind of calculations we've been able to do. I just put this Horava Jimon paper in the chat.
Oh, yeah. Okay.
That just suggested to me that maybe when you get up to this boundary, you start seeing more interesting things in the sense that you put the brains in the geometry, they resolve the CTC and allow you to then go further out. I thought that was I've forgotten that paper because it's been a little while, but I thought that was their point, that anytime you come to something which wants to form a CTC, a brain becomes light and descends down. So if you put a super tube inside the geometry, you cross barriers. So
I see. It's possibly, I talked when Juan asked this question, I said the problem with gravity is it has too few degrees of freedom to see interesting physics, and I think you're making the same point. And it really is that we've frozen out so many degrees of freedom in order to go straight to a solution. And I think by allowing a few more degrees of freedom, we should be able to cross these barriers. And particularly the thing I'd love to be able to do in some weak form is to take a superstratum and an antisuperstratum and have them interact with each other and settle down to a ground state. And that ground state should be time independent or close to time independent. And that's the kind of state that I think might cross that barrier very well. Because there the QP will be very small, but the mass will be large because there's all the fragments left over from the annihilation.
Okay, great. Thanks.
I see Andrea has her hand up. Please go ahead.
Yes, I'm not familiar with the 3D language, but I wanted to ask, I can think of these non-BPS solutions as non-BPS excitations that use momentum and anti-momentum traveling in the opposite directions, as opposed to having charge and anti-charge, which would back react into a new bubble. Is that right?
Well, QP, is it a charge or is it momentum? It's a semantic point. What's going on here is that the superstratum has a momentum that's exactly on the light cone, and an antisuperstratum has a momentum that's exactly on the other light cone. These have a momentum that is inside the light cone, and so it's got a QP, but it's got more mass than it has QP in that sense. So that's what this diagram is supposed to tell you. Where's it gone? This sort of last phase diagram that I drew. Yeah, here. So the superstratum, this purple curve is the superstratum. For a given QP and a given Q1 and Q5, this is the BPS bound. And everything we've got is in here.
Yeah. But so I guess what I'm asking is whether you create by this process multi-center superstrata or just it stays the superstrata.
I'm laughing because wouldn't it be nice, but boy, is that so far away from what we can do numerically.
So it stays a superstratum, and it's not like what I meant by the distinction between the momentum and like other brain charges, where you put we had like these anti-brains put into existing microstates, which would back react and form, create more bubbles. So this is not what you're.
No, this is just the most plausible way I can think of getting to non-BPS microstate geometries within the framework of the D1, D5 ADS CFT that I know how to do. Ideally, David and Samir wrote this paper some time ago where they argued there might be a way to get Q1 and Q5 to sort of have a distribution that rotates at large spatial separations, and so the net charge is 0, but locally it looks like it's BPS. There are many things you can imagine trying to do. At some point, you've got to do the triage of what is the doable versus what is the dream that you would like to do. And so by trying to push beyond the BPS barrier, we've very, very strongly been influenced by the doable.
But isn't it also the most typical sector anyway? Like
yes,
few bubbles and
yes, it is. So you'd think that
there's a Goldilocks.
We don't know, actually.
Sorry?
We don't know if it's more typical to have a few bubbles or more bubbles. I mean, we can build superstrata which have like, single bubble, but just because you cannot build 3 bubbles or like, 3,000 bubbles with fluctuations, we don't know. So
yeah, I would say, how am I trying to do this? I really did think of it in the terms of these sort of Rube Goldberg things. We've done a bunch of things whose sole purpose is to make the numerics doable. It's not to expose, not a priori to expose the physics. We tried to just make the numerics doable. And so we went to this very special class of reduced superstrata, and we put various particular phases in them. And yet we still found some interesting physics. Well, we found that there were solutions that were there. That is non-trivial already. The fact that you're turning on the break the supersymmetry, you've got solutions and they're perfectly happy and smooth and regular. And you turn on mass above charge and they're still there. Also, we found this frequency shift, which I think is really cool. But as I say, I'm not saying these are the solutions that must be microstates that you should study. These are incredibly specialized beasts. But at least they're beasts in the right trajectory. Now once we've got this sort of starting point, we can start trying to look for physically more interesting, physically more robust or solutions which involve, say, scattering of that superstrata and antisuperstrata. And I think that's sort of place we're going to go next, now that we know we can do it. The important thing for me was to know that we could do it.
Okay, let's have 2 more questions before we wrap up the main session. We can conclude informally after we stop, but Nyash was first and then Emil.
Hey, well, thanks a lot. Very, very interesting. I guess I wonder whether you can connect the second part of your talk to the first part in terms of the echoes. I mean, how do you think that the echo conclusion you had with basically the stringy modes falling in, how would that change in this picture, or would it change?
So I have to be very careful in the sense of I've built superstrata, these microstrata, they're incredibly special. So let me just show you that this picture sort of kind of says it all. Look at the geometry. These are the geometric functions that matter. So this is the coefficient, this is the warp factor in front of the spatial metric. The superstratum has a little kink in it. This guy has a couple of wiggles, but it doesn't change very much. Now, maybe these wiggles have some physics in them. Similarly, the coefficient dt squared, that's the superstratum, it's 1. This has a little wiggle in it. K, the angular momentum vector, now this is a bit deceptive. The differences are small on this sort of order. So the geometry hasn't changed a whole hell of a lot. What has changed is the depth of the geometry as it's controlled. The parameters, remember I called them A and B before, we now have a third parameter, omega. And so you can shift the depth by moving around with omega. So I think the core message still hasn't changed. The geometries are very similar. They're deformed in interesting ways, but I think everything that I said before will happen in these geometries. But I am not going to claim these geometries are in any sense typical. These are the geometries I can get to. but they should be. They should be in the. I think the interesting thing for the holographic, the people who work on the ADS CFT is what the hell's the CFT dual of these things? And I want to stress particularly for them that the numeric perturbation, the perturbation theory, is surprisingly accurate. So you can do perturbation theory in the gravity side, and I'm sure there is an ADS CFT dual of precisely this set of statements, this sort of thing. So I think the first thing I'd say about this that's maybe cool to explore is to go try and do some more precision holography on these things. These are very special, highly tuned states. At some point, though, one should be able to do something which is much more interesting, I think, which is where you run a superstratum in one direction, a superstratum in the other direction, have them collide.
Sure.
And then that might settle down to something much more typical. And I think something like that is maybe within reach. But you know, I find this part of it really, this sort of thing really intriguing. I'm already seeing clues as to what the bigger picture is once you go non-BPS.
Great, cool, thanks.
Thank you.
Okay, Emil?
Yeah, lots of questions, but let me just ask one or two. So, so what you're solving here are some differential equations in some kind of ADS reduction of the full 10-dimensional.
Well, it's that thing. It's a 3-dimensional supergravity,
right? Which
has ADS. So that's the Lagrangian.
Okay, so I'm trying to get a handle on how messy these things are. So, is there any hope that you would be able to compute some small fluctuation spectrum around one of these things?
Yes, I think that's doable. What I've come to be impressed by, and Bob has really taught me a lot in this respect, is just how difficult it is to do numerics of things. But once you have a solution, even if it's a numerical solution, you can do linearized analysis about those solutions. So yes, I think that is a doable thing. But what you have to do
many people who do that, by the way. So this is actually very standard. People who do ADS-QCD, you know, they have numerical confining vacua, and then they solve around them, and they find meson spectra.
Okay, but the thing to do is to find the most interesting solution to do that about, because it's, you know, and I'm not going to claim that the solutions we have at the moment are the most interesting. I think there will be more interesting ones that will come out of this process in the future.
It was more just a sort of a question of principle of whether these solutions are at least marginally stable, or whether they're actually unstable because of some.
If they were unstable,
or are you working in sufficiently restricted ansatz that there might be some instability?
Let me answer that question. There's an easy answer. If they were unstable, the numerics would have utterly failed to converge.
Unless they're unstable in some modes which are being thrown away in the consistent truncation.
That's entirely possible. That's possible.
No, because you're in ADS.
When we first started doing this, we found it stable. So let me answer the questions. When we first started doing this, we started finding that we couldn't get any decent convergence in the numerics. And then we realized that there was some physics that we were missing, which was this whole idea of resonance. So typically when we first started doing this, our numerics were horrible. They were sort of 10 to the minus 4 errors, 10 to the minus 5. And then we suddenly started finding that the numerics converged beautifully the minute you tuned the frequencies of the resonant value. So I would say that if there's any instability in the action that we're using, the numerics will almost certainly fail to converge. But
I think because you're in
whoa. But that's for some specific scalar fields that you're trying to solve, right? Yep. So there's a more general problem, which is what are all the supergravity modes that are fluctuations around that?
Yes, fair enough. Absolutely. And
right. So there's something you would call some kind of matter fluctuations around the background,
right?
In some other, you know, pieces of the dimensional reduction of supergravity, and you have to check that all of those are stable as well.
Right, and that would be the work for an army of graduate students. But it's I suspect that how to put it, the ones you have to check are probably the low mass sector of the things that are in the 2B supergravity.
Well, the kind of thing that I would worry about first off is that the sort of the background of this is some number of plus strands,
yep.
And the initial depth of the throat is governed by the number of those, the fraction of the strand budget that you devote plus strands. And the kind of thing I worry about from time to time is, can there be a process by which the supertube offloads its angular momentum onto some other supergravity excitations? So the number of plus strands goes down, A goes, the little parameter little a in the solution goes down, and the throat gets deeper. Right. And so, you know, can the system run away in that direction if you're supplying it energy above extremality? Can the depth of the throat sort of go to infinite redshift?
I think what's happening here is that, so there's another answer to that question, but I want to frame that question in another way, because we see evidence of that in a different way. Because we're requiring there's a cap and we're putting boundary conditions that require smoothness at the cap, then you won't see the runaway in that direction. But if there's such a runaway, you will see it possibly here. And this might be a hint of the kind of thing you're alluding to, that because we put a cap at the bottom, because we insist on smoothness at the cap, the error or the problem is going to occur somewhere else. And the somewhere else is classically towards infinity. As you get this is infinity, remember, the things that the Y circle become closed time-like curves. That's the signal that something is seriously wrong with the solution. And so these solutions, the minute you try to get above this bound, say, they don't work. And so we can't get above that bound. And that might be related to the question you're asking, that from the way we're setting the problem up, we're not letting the bottom fall out of the market. Although we could, because we're imposing boundary conditions on these 11 fields that say the damn thing's got to wind up smooth in the cap. Pretty much, I'm not 100% certain that we've excluded all possible singularities in the cap. But then, as with all these things, if you impose some regularity in one place, typically the problem bites you somewhere else. And the way it typically bites you is through CTCs. Mm-hmm. And so the kind of thing you're worrying about is precisely going to manifest, I think, in this appearance of CTCs. And so the question I think you're asking about is, I'm managing to load up the mass, and I'm trying to get up in here, and I find there's a barrier. And maybe that's exactly what you're alluding to. But I would stress that this is because I built the modes in such a strange way. And I think there are solutions out there which, put it like this, if I have a superstratum and an antisuperstratum, they run into each other and they relax to some set of scalar excitations, I should be able to build those scalar excitations and their back reaction at the bottom of the throat. I should be able to do that. And it's possible that when you get sufficiently high energy, there is some phase transition. And what that phase transition is anybody's guess. But if you're a gravitational physicist and you believe only in GR in 4 dimensions, say it forms a black hole. However, we've learned so much from the whole Superstratum fuzzball program that phase transition will possibly involve activation of, as Samir said, there's possibly some super tube that drops down, or some new brain that appears, or some W brain start condensing. There could easily be a phase transition. And what that phase transition is, we don't know. And it could be intrinsically stringy, at which point the supergravity will fail to work. But I would prefer to frame it not in terms of forming a black hole, but in terms of there is a phase transition, and what does that phase transition involve, and how can we describe it?
I think Emil's point also fits in the swampland framework. So the swampland, somebody who's on the swampland side would say that all solutions which are non-supersymmetric and asymptotically ideas or asymptotic something should be unstable by some sort of mechanism. So I think Emil's question is also, whether there's an instability, which I think there are two questions which are different though. Is there an instability, and do you collapse into a black hole? So Juan is actually asking on the chat that, essentially there has been a discussion going on whether if you add some energy, because there's a direction which makes this throat longer and longer, why don't you go there? And, if you put some energy, then the energy will drive you in that direction and form a black hole. And I think Nick's...
Okay. It's the and form a black hole. That's saying, and if I describe it in general relativity in 4 dimensions, it will form a black hole. We know that. But the thing that we've learned from microstate geometries, the thing we've learned from string theory, is the and form a black hole is wrong.
Okay, maybe this is a good point to continue informally and off YouTube, but
yes, I'll stop.
Maybe it's an appropriate time to thank Nick for a very nice talk.